Right, so in this video, I'm going to talk about Thevenin's theorem. We're now moving into chapter 4 of the textbook, and so far you've been introduced to superposition and source transform. As you may be aware, these are all theorems that you could use to basically solve for a much more simplified circuit. So what is Thevenin's theorem? Thevenin's theorem says that we can reduce our circuit, assuming some sort of black box system. We can actually reduce the circuit all the way down so that we could actually simplify it to only become a series circuit. Essentially, this is what you call a voltage divider, which you've seen before. Voltage divider, basically, if you have a voltage and two resistors in series, and you're trying to just find the voltage across one of the resistors, therefore, that's just a method of voltage division. So that's basically the idea here is given some sort of circuit, this is what you call a black box. You may not need to know or worry about what is happening in your circuit, but it's a linear circuit. We'll kind of talk about later on the difference. If it's not a linear circuit, then what do? You have current going out, and then you have some sort of load resistor. So a load resistor by definition is basically it's the component or some sort of device that you'd be, let's say, recharging or something. You could consider that to be what you call a load resistor. All right, so if you can convert this all into this, then you've successfully performed Thevenin's theorem. Now in Thevenin's theorem, two things you're essentially looking for are Thevenin voltage and Thevenin resistance, and that's denoted here by VTH and RTH here. So how do you actually go about in using Thevenin's theorem? So just like many of our methods before, there's a systematic step-by-step approach that we like to use. So in this case, if we follow these steps here, really just, well, 3 steps, sure, you can break it up to smaller steps, but 3 major steps. First is finding RTH, second is finding VTH, and then you want to create the new Thevenin circuit, which is this model here. And you want to go ahead and solve for whatever it is you need to solve for. So let's go ahead and take this step by step. So given this circuit here, maybe what you can do is, maybe before I even do this, go ahead and pause the video and try it for yourself. All right, so moving on. Step 1, find RTH. So in order to find RTH, what you want to do is you want to do the 2 things here. First, remove your load resistor and any current sources, literally just take it out. And the second step is you want to short the voltage source, okay? So let's go ahead and do that. So if I want to short the voltage source, I'm just going to basically just draw a line over it. So imagine if I just did that, that's called shorting it. So I'm going to short that. I'm going to draw my first resistor. I'll go ahead and put in values a little bit later. Second resistor like so. And then I'm going to remove the current source. So I'm just going to create a little circle there just to show you that something is missing, but it's also not connected. Then I have another resistor here. And then the last part, we aren't going to reconnect the end like so. I'm going to label the top as A. I'm going to label the bottom as B. I'm going to write in my values here, 4, 12, and 1. These are on ohms. And the question now is, okay, so how do we solve for RTH? Where do we begin? Well, the reason why I labeled A and B is because we can go in this direction. So we want to go from A and all the way to B like so. All right, so what I can do now is I can combine the circuits or combine the resistors here and reduce this down so that we can find the Thevenin resistance or some sort of summary resistance here. So in this case, if I were to reduce it down, I have, starting from A, I have 1 ohm plus, since this is a parallel connection, I'm going to use my shortcut 4 times 12 divided by 4 plus 12 like so. And then what this reduces down to is 1 plus 3, and that's equal to 4 ohms. Therefore, just so you can visually see what's happening, I basically reduced it down to this, and then AB like so. So then what does this mean? RTH is equal to 4 ohms like so. All right, so we did the first one, or the first step here. Second step, find VTH. Again, feel free to pause the video here, and then you can kind of continue working on from here. Second step here, what we want to do now is we want to find Thevenin voltage. And in here, what we want to do is we want to begin with the circuit again, but then we now want to remove RL, and then we also want to find VAB. So what does that mean? So when I say remove RL, we are going to remove the load resistor, and then we're going to find the voltage across A and B. So what does that look like? So what I'm going to do now is I'm going to redraw the circuit so you can follow along here. So you have voltage source, up and across, down, resistor, across here, current source, connect it all together like so. I have my 1 ohm resistor like so. And then now where I used to have a load resistor, I'm going to go ahead and just do this. And then essentially what I want to do is I want to find VTH. So what's the voltage across A and B? Let me go into write my values here. So 1, 2, 12, 4, and 32 volts like so. All right, so here, how do we solve for your VThevenin? Well, what we're going to do is we're going to use nodal analysis to solve for this. So let me do a different color. So the node that I want to look at is this right here. So this is going to be VTH. In fact, the entire top row is actually going to be VTH. So I have I1, I have I2 going out this way, and then I have I3 going this way like so. So my nodal analysis will tell me that I1 plus I3 is equal to I2, right? All right, so then what I want to do now is once I have my node equation, I'm going to go ahead and identify what each of the node means. So I1 is equal to 32 volts minus the unknown, so VTH, all over 4 ohms. So this is happening on this side of the circuit. I2 is going to be this right here. So that's equal to VTH minus 0, which is down here. This is actually the ground. Sorry for forgetting to write that. VTH over 12. And then I3, since it's the current source right here, is just equal to 2. Like so. All right, so then when we go ahead and substitute all these back into this equation here, what we'll end up with is this equation. 32 minus VTH all over 4 plus 2 is equal to VTH over 12. Okay, so what I'm going to do is I'm going to multiply this by 12 so I can get rid of the denominators. And then what I'll end up with is 96 minus 3 VTH plus 24 is equal to VTH. So I do this just to simplify things for myself. All right, so simplify all this, and when you solve for it, what you end up with is 120 is equal to 4 VTH. So VTH, or Thevenin voltage, is equal to 30 volts like so. All right, so that's the second step. So we found Thevenin voltage here. Now the last one is you want to just go ahead and use the model up here, create the circuit, and then plug in the values that you found for VTH and RTH. So for step 3, so I'm going to take my model, which is source, resistor, resistor. So this source is now VTH, this is RTH, and this is RL. So what are the values? So VTH, as we found before, was 30 volts. RTH is going to be 4 ohms. And then the load resistor is going to come from the original graph, the problem, which is going to be 5 ohms like so. So what we're looking for here in this case is going to be the current. So what is the current that's going into your load resistor? I believe I forgot to say that, but that's essentially what the problem is asking you there. So what's the current going to the load resistor? So I is equal to VTH over RTH plus RL, which is equal to 30 volts all over 4 plus 5 ohms. So then when we actually solve for the current, is equal to 3.33 amps, like so. All right, and that's how you use Thevenin's theorem.